Okay, class. So we will have in total 7 classes, including today's class. Out of these 7, we will have one test, which is on next week's Friday. I don't know the syllabus yet. Before up to that point, whatever I will cover, that will be the syllabus for the test. And so basically, we'll have 5 classes from now. And today we'll start the last module of this course. And that is the most fun module of this course because finally you will see some application of all the principles you have learned, like momentum conservation, mass conservation, energy conservation. So for this module, what we will do, we will try to analyze and design the pipe flow or the flow inside any pipe system. Okay, so that's what we will do. And for this class, we will do the design for any types of fluid. It can be water, it can be any heavy oil or anything. And this lesson will continue to your next course, which is the water resource engineering you're taking next semester. There we will continue all of this pipe flow, but that time we will only work with the water. We will not deal with any other type of fluid anymore after we pass this course. Okay. So that is the thing for today. And just to remind you, I sent one email, but that was during a ring figure ceremony. So I don't expect you to remember all the details there. So since for ring figure ceremony, we couldn't have an in-person class, I recorded a class lecture that's uploaded on YouTube. And there is a quiz you need to take after watching that video. But that is due on Wednesday. So you kind of have today, tomorrow, and Wednesday. I just sent another email just to remind you so you can get all the links there. Okay. Okay. So for today's class, you all should have one class lecture, a thick class lecture, because that is the lecture for next 3 class lessons. One class examples, which is class example 22, and one packet where you have a table, some diagrams, and some pictures. Do you have that, all of you? Okay, good. So what we will do, so basically you should have 3 different printout today. So as I said, what we will do for this part, we will try to identify what are the reasons for the head loss. How can we incorporate that into the design? How can we make sure at any point the pressure is adequate or the diameter of the pipe is adequate or something like that? That's what we will do. And just to start that, let's use a very common example. This is a pipeline in between US and Canada. What is the name of that pipeline? The Keystone Pipeline, yes. And that actually carries the oil from US to Canada, right? And this is the map, like it starts from here to here, and it's almost 3,000 miles long. So that's huge pipe, right? Pipeline. And if you look at here, you can see there are lots of bends, lots of joints, at the same time, elevation difference, temperature difference in different region and everything. So if you were an engineer for that design project, what are the things you needed to consider? The materials, yes. Temperature changes, yes, that will change the viscosity of the oil inside the pipe, right? At the same time, you need to head loss, yes, because what you are supplying and what the pressure other end are getting, that is important, right? So you need to consider, okay, you are supplying with maybe 1,000 magnitude something, but the other end is getting 900 magnitude, but they need 915. So you need to design that way, right? At the same time, you need to check the carrying capacity of the pipe also, like whether this pipe is wide enough to carry the required amount of oil or not. So all of these things we will try to discuss briefly, not in very details, but briefly in this part, okay? We will try to identify what should be the diameter of any pipe for any required flow, what are the system or energy loss, and how to incorporate that into design, something like that. That's what we will do. Now, this is just one example, like the commercial purpose. For any building, you need to do the plumbing design, right? That is another type of pipe setup. For any industrial purpose, you need to do the pipe design also. So these are just few examples where you need to know the pipe design components and everything. So just think about the plumbing system. If you turn on the faucet in your like washroom and the pressure is not adequate, obviously you will not feel good, right? And maybe you'll say, what a bad design, like engineer designed that, like there is not enough pressure or something. So we need to make sure that the pressure at the user end is adequate so that you can use that properly, right? So since this is the very first class of this topic, so we will try to learn lots of new terms and everything. So bear with me, and from next class, most probably we will do lots of mathematical calculation. Okay. Okay. So this is a picture from the Venturi meter. You remember you went to lab and we tried to understand what are the head loss and energy loss and everything. And you did one homework also, right? So what you did here for all of these 11 manometer, at first, we knew the pressure head, right? And then using the diameter, we calculated the area, and using area and from the known flow, we calculated the velocity head also, right? And since for each pipe, the elevation head was same, what we did, we add these two plus elevation head, and we finally found total energy head, right? Now, we said that at any point, the energy should be same, but that's not what we are seeing here. The energy is not same, it's declining with length, right? That means the more length the flow is traveling, the more loss the system is getting, right? So to how do we can identify these loss at any point, and what are the possible reasons for these loss? That's what we will try to identify. Okay, so this is called head loss or energy loss. Okay, now what do you think, like what can be some possible reasons for head loss or energy loss? What do you think? Friction of what? Friction between fluid and like the pipe surface roughness, something like that. Okay, so one can be friction. Okay, good. What can be other possible reason? Say it again. For temperature, it can be that can be that is, yeah, that can be like due to viscosity. That can be one thing, and within few minutes we will see viscosity is another form of friction also. So I will just write down in two ways here. One is fluid and solid surface, and another can be fluid friction. Okay, and the viscosity can play a part on that. What are the other reasons? Do you think I'm just giving you one similar example. So when you drive a car in highway and in a local road, in which way you can get more mileage, in highway or in local way? Why is that? because you don't stop that much, right? At the same time, you don't have any sharp bend or something, because the way they design highway is all the like direction of like road, it's kind of very mild, so you don't realize that, right? Exactly same reason, the flow, if the flow can like continue like smoothly without any break or any significant direction change, you will have less energy loss in the system. The same reason, because when there is a sharp bend, you have to stop or you need to reduce the velocity or something, and then you need to take the turn, right? So it's the same thing. If there is any irregularities on the way of the flow, the system can have some energy loss. Okay, so it's a very good similarities with any like car flow or something. That is another type of flow. So the reasons are kind of same. If you drive on a gravel road, obviously you will feel more bumpy, and obviously that will create more energy loss. At the same, it's the same thing if flow goes through a pipe where the pipe surface is not smooth, obviously there will be significant amount of head loss also. Okay, so what we will do, I have some pipes here, different types of pipe material. So this one is the PVC pipe, obviously the most smooth one. We have copper pipe here, the old copper, so it's rusty, and at the same time, the roughness, you can feel that. And these are two other pipes. You can just try to feel the roughness. We are not measuring anything here. So that will help us to understand the pipe surface roughness. Okay. Now, what we will do, before I go into very much detail, don't hit your head. So what we will do, at first, we will try to write down the summary and like to identify different types of head loss. And then we will go through very briefly for each type of loss, so that at first you will have the summary that is kind of the full picture, so that you can connect with the explanation. Okay, so maybe for your copy the space is not enough, but adjust that. Okay, so the first one is, obviously we are working with head loss, and we can have two types of head loss here. The first one is major loss due to friction. The another one is minor loss, any close way. Okay, so these are two main division of head loss. Now, when we say due to friction, there can be two types of friction, as I said briefly a little bit ago. The first one can be friction between fluid particles. The back, can you see the text a little bit? I think the very last, you can't see the text, right, Derek? And another type can be the friction between fluid particle and the pipe surface. Okay, so friction between fluid particles, what can be the indicator for that one? How can you, like, what is the indicator or what is the thing you know about friction between fluid particles? Is there any property you know which will, the viscosity? Yes. So the friction between fluid particles, that is actually viscosity will be the one which will give us the quantity of that one. So that is the viscosity, and there is a number called Reynolds number. Okay, Reynolds number is the indicator. So Reynolds number can actually tell what amount of viscosity is present within one type of flow, and based on that we can identify different types of flow. We will discuss that one. And for friction between fluid particle pipe surface, there is another thing called epsilon over D, which is relative roughness. Okay, so D is the diameter, you know that, but you don't know the epsilon. What is epsilon? Here it's not strain, but the notation is same. This one is, so all of you experienced a little bit like roughness inside the pipe, right? So suppose this is the pipe, and if I try to draw roughness here on both sides, okay? So the depth of this roughness, that is actually the epsilon, okay? Okay. So this depth of surface roughness is actually the epsilon, and this epsilon is well established for all the common pipes, so we can get those values from the literature. We don't have to measure all the time. Okay, so these are the reasons. One can be the viscosity, and another one can be the pipe surface roughness. Those are the reasons for the major head loss. And for the minor head loss, there are lots of things. We will try to identify the top 5. So I will just write down those and we will discuss those briefly. So the very first one is entrance and exit transition. We'll discuss what does it mean. The next one is expansion and contraction. The next one is pipe connection. Any sort of bends and valves, they all can create some sort of minor losses. Okay. In easy word, any irregularities on the flow's way that will create the minor losses. Now, from the name, we say that it's minor loss, which simply means this, the magnitude of this loss may be small compared to the friction loss, but that's not the case always. If you have this amount of, like this length of pipe and with 2 valves or 2 bends, obviously the minor loss will be the dominant one. So it will depend on what type of arrangement we are having with all the valves and bends and everything. Okay. Okay, so this is just kind of the summary we will discuss for today's class. Now what we will do, we will try to go through each one very briefly, but now you have the summary, so you can always come back and connect with this one. Okay, so when we'll discuss about the major loss, the frictional resistance. For majority discussion, we will always use the circular cross section, okay? Because that is the greatest structural, like that has the greatest structural strength. At the same time, it can transport the largest amount of water or fluid with the smallest frictional resistance. And for any regular use purpose, like for plumbing or any other use, we usually use the circular one. So that's a good way. But if we have any other type of shapes, how can we incorporate all the equations? We will learn that too at the end of this class. Okay? So for major loss, obviously, we can calculate the major loss by just do some experimentation, and obviously the energy equation is the one what we have to use. So let's try to find out what should be the expression for the major head loss. Okay, so this is the energy equation, the most comprehensive one with turbine pump and everything. We will just consider a section of pipe, a circular pipe. This is 0.1, this is 0.2, in and out. It's a uniform cross-section pipe, so there is no change in diameter. Okay. Now, in between 0.1 and 2, is there any pump or turbine here? So there is no pump, no turbine. These two are 0. Okay. Now, the same Q is going in and going out, and the diameter, like D in and D out, they are same also. So do you think there will be any change in velocity? Same Q, same diameter, everything. So the velocity will be same. So what we can do, we can cancel the velocity because they will be same. Now, one more thing we need to consider. Let's identify the center line of this pipe. And maybe this is the datum. Okay. Now the datum is horizontal, the pipe is horizontal. So at any point, we will have same Z, right? The elevation head. So again, we can cancel Z1, Z in and Z out. So finally, we are having the head loss P in gamma delta P, or difference between 2 points, gamma, or pressure drop. Okay, so that is basically the equation for major head loss. That means if we can quantify the pressure drop between 2 points, we can calculate the major head loss. Okay. Now this major head loss, as we said at the very beginning, that it depends on the friction between fluid particles and friction between particles and pipe surface. It will be different for laminar flow and turbulent flow. Okay. Do you remember laminar flow and turbulent flow a little bit? We discussed a little bit. So again, from lesson 22, the laminar and turbulent flow. Laminar flow is the one which is very regular and like calm and quiet flow, right? Like this one here. There is no eddies or no bubble or something like that. And the turbulent flow is where you have so much chaotic flow, lots of bubbles and everything here. So obviously you can say for these two types of flow, the head loss will be different also. Now, if we can see the flow, we can identify maybe a little bit what type of flow we are having, but there must be some mathematical way also to identify these types of flow, and that way is actually the Reynolds number. Okay, so the Reynolds number can identify whether we are having the laminar flow or the turbulent flow. And the Reynolds number is the ratio between inertia force over viscous force, rho v d, and the mu. What is d? Diameter, or it can be any other characteristics, length also. V is what? Okay, what is? Okay. And this one is obviously the viscosity, dynamic viscosity, right? Okay, now, what is the reason for having a laminar flow? Like why the laminar flow is very smooth and everything? Say it again, sorry, I didn't. Turbulent flow can be uniform also. I'm giving you one hint. Can you imagine a flow of honey with turbulent flow? Because it's too slow, but why it's too slow? High viscosities. That is the reason for having a laminar flow most of the time. Either the velocity is very small or the viscosity is very, very high. Okay, that is the reason for the laminar flow. Now, if you look at the Reynolds number, it's inertia force over viscous force. And for laminar flow, viscous force is very high. Okay. Now, just can you give me one answer? For laminar flow and turbulent flow, for which one the Reynolds number will be smaller? Just look at this expression, inertia over viscous. Higher or lower? It will be lower because you can see the viscous force will be very high for laminar flow. That will give the Reynolds number the smaller magnitude, right? Okay, we don't know the number, but just can we did we get the idea that for Reynolds laminar flow, the Reynolds number will be less than the Reynolds number of turbulent flow, right? Just look at this expression. Viscous force is on the bottom side. So if you have a high viscous force, the number will be lower, right? Okay, now the next task is how can we find what will be that number? For most engineering application, laminar flow for the Newtonian fluid begins to change to transitional flow about that 2300, and this value is called the critical Reynolds number. Therefore, the laminar flow occurs when the Reynolds number is less than or equal to 2300. Okay. Now, in real, this number is actually from 2200 to 2500 based on different experiments. The book we are using in this class, they use 2300. That's why we will use 2300. But if you see 2200 or 2500 in any other book, that is fine also. Okay. Okay. Now, let's identify what should be the equation for the laminar flow and the turbulent flow. For the laminar flow, using different analytical method, we can get the equation, and that equation is head loss for laminar F L over D B square over 2G. Okay. And if that is a circular pipe, what is L? What is L? Length of the pipe. I finally found what is the reason of that extra line. It's the capacity of that CPU. No, F is just some parameter here. Okay, and D is the diameter or depth, right? G is what? And the V, any type of velocity or the velocity perpendicular to the area, right? And this F, that is called friction factor. There is another name, Darcy friction factor. We will discuss why it's called Darcy friction factor, but this F is the friction factor. And for laminar flow, the friction factor is only a function of Reynolds number, okay? And it does not depend on the roughness of the inner wall of the pipe. For the turbulent flow, we will have kind of same equation, but that equation was developed from the experimentation. So there is no analytical basis for that. Everyone's done with this equation here? Okay, so for again, F L over V square over 2G, the same thing equation again. V is perpendicular to A, and the friction factor, F is the friction factor, but this time friction factor is function of Reynolds number and epsilon over D. That means it will depend on the fluid friction, at the same time fluid solid friction also. And you can see why the turbulent flow is difficult, because it depends on so many things. Okay, now the funny thing is, the previous equation, it was developed from analytical method. This equation, it was developed from experimentation, but it comes out that they have the same expression. Only the F depends on different things. Okay, and this equation is called Darcy-Weisbach equation, based on two scientists who actually developed that one. And the Darcy equation, when you will take the soil mechanics next semester, you will see Henry Darcy did lots of things for soil mechanics. You'll see our equation like flow through the soil, and his equation is everywhere. Okay. Okay, so these are the equations, and now the thing is, we can measure L, we can measure velocity, we can measure everything except what? Friction factor, F, right? So now the next task is, how can we calculate the friction factor? That's what we will see. There is a diagram called Moody's diagram. This diagram will help you to get the friction factor, okay? And it's important to understand this diagram, because we will use this diagram for rest of the semester, like next 5 classes, we will use this diagram a lot, okay? So it's important to understand. Now for Moody's diagram, instead of 2 axes, we have 3 axes here, okay? 1 X and 2 Y axis. So let's identify the name of each axis, okay? The very first one is what? Friction factor F, right? What is the next one? The Reynolds number. And what is the last one? epsilon over D. So we have three different axes and all of these are non-dimensional quantity. That means you can use this chart for any type of, like any unit, SI unit, FPS unit, it doesn't matter because Reynolds number is unitless, F is unitless, epsilon over D is unitless. Okay. Now, let's go through very quickly for different zone of this chart. The very first one is what? Okay, one thing, just make sure you can read the chart, all the text and everything, because we have to use that for mathematical calculation. Can you see, can you read the text? You don't have that? Here. Anyone has this one? Okay. Sorry. The second page of this one. The second page of this one here. Just make sure that you can read the numbers and the text because we have to use this chart. Okay. And can you see on top of that chart, you have the epsilon for all the usual pipe material and everything. So we need to use that one also. Okay. So the very first one is what? The laminar flow, right? After that, what is that zone? Here, the critical one. So the critical one is very unstable, and that's why it's the critical one. After that, what zone you have? The transitional one, because in this zone, flow can be laminar or turbulent depending on different scenarios. That means flow is transitioning from one type to another type, and that's why this zone usually the transitional one. And after that, from this line, you have what? Fully rough turbulent flow. Okay. Now for laminar flow, the F is 64 over RE. And you see in the equation, there is no epsilon, nothing. That means it only depends on the laminar flow. Now, tell me one thing. Are you seeing from this line, like this line, all the lines, they are horizontal kind of? What does that mean? Here, all the lines here, they are kind of horizontal. Here, what does that mean? Why we are having horizontal line for different Reynolds number, and what does that mean? So, okay, let me help you. For this Reynolds number, the same value, this Reynolds number, same value. That simply tells you that Reynolds number is not doing anything there, right? That means when the flow is very fast and very turbulent, viscosity is not playing that significant role. And that's why for any Reynolds number, you will have the same value. But here you can see for different Reynolds number, you can have different values. That means up to this zone, the Reynolds number is playing something, but after this one, that is kind of invalid. Okay. And that's why for turbulent flow, mainly the epsilon over D, that is actually the main thing to consider. Okay. Okay. Now, all of the things here, we did that for circular pipe. Now, for some reason, if we don't have the circular pipe, how to work on that? No, how to work on that? That's what we will do very quickly. So, for non-circular pipe, what we can do, we can use another parameter called hydraulic diameter. Instead of diameter, this time we will have the hydraulic diameter, and the hydraulic diameter is area and area over perimeter. Okay. Now the Reynolds number, the actual Reynolds number was V. Okay, I missed one thing. This is the equation, right? Now this D is obviously for circular pipe. If the pipe is not circular, we need to use this one. Now let's check how that D and DH are connected. So for circular pipe, what is the area of the circular pipe in terms of D? Pi D square over? Okay, 4. And the perimeter is 2 pi r or pi D. Yeah, so you can cancel pi D. Finally, you will have D over 4. Yes. That means that is the relation D equals to 4 DH. That means if I want to write down the same equation for circular pipe in terms of DH, that will be the one. Okay. Now for the rectangular pipe here, if this one is B, this one is H, what will be the DH? A is BH and the perimeter will be what? Okay, for this case, that is the one. But for open channel flow, sometimes the top part is open and we consider only B plus 2H. We will do that when we'll do the open channel flow. So that is the one. That means the Reynolds number will be rho V 4 BH okay. But the good thing is for most of the time we will work with the circular pipe, so maybe we don't have to use the hydraulic radius all the time here. But when we will work with the open channel flow, since the open channel flow channel shape is not circular or nothing, that time hydraulic radius is or hydraulic diameter is very, very important. Okay. We have 5 minutes. So what we will do, we will just go through very quickly what are the different sources of minor head loss. Okay. All of you are done with this equation. Okay. So as I said, the minor loss, most of the time it's insignificant to the major loss. That's why it's called minor loss. There is a thumb rule. If the pipe length and diameter ratio L over D is more than 1000, minor loss can be ignored. And you will see that message sometimes that, okay, ignore the minor losses, something like that. So the minor loss equation is summation of KL is square over 2G. Again, B is perpendicular to the area. And this KL is minor loss coefficient. And the packet you have, there is a table, some pictures for KL for different setup. Based on what we are doing, we'll use KL from that table. Okay. And usually they determine this KL experimentally. So we will discuss 5 major sources of minor losses. The very first one is inlet and exit transition, like when the flow first enters into the pipe or it exits from the pipe, there can be a loss based on what type of setup we are having. You can see number C is the highest KL, right? Because of this extra portion, because that will create more irregularities in the flow. Next one can be expansion and contraction. So whenever there is a contraction or expansion, there can be a loss here. But if you can make that like gradual, obviously the loss will be less. Any type of bends, obviously that will create some loss. So one way to prevent or reduce that loss is sometimes they use the guided vein here. So flow is kind of guided. It's not sudden, like there, it's not detached from the pipe or something like that. That can be another way. Any type of wales, even glue, thread, that can create the irregularities. And the valves, the last one, any type of valves that can create the head loss also. I have different types of valves here. Like this is one type. This is one type of with a strainer. Here is one, just one way. Flow can go through this way, but flow can't go that way. Okay. This is another one. Now, give me one answer. This is partially open, right? And this is fully open. Now, for which one you should have more head loss? This is fully open, so water can go through this way. And if I make that like partially open, so which one will create more head loss, partially one or the fully open one? The partial one, because there are like different type of surfaces, different types of openings and everything. So that's why it can have more head loss here, depending on whether the pipe is fully open or closed. We will take the KL value, and for in your table, you can have different types of KL value also. Okay. Just one more thing. Go back to your that summary table here. Just write down two things, then this summary table will be complete. So the major loss, F LD V square over 2G. And for the minor loss, this one is KL okay. And this F, I just need 1 minute. Laminar flow is F equals to 64 over RE, and the turbulent flow F Moody's diagram. Okay. So this summary table is complete. What we will do in next class, we will do the mathematical problems. Please bring your class example 23 and the packet I gave you. Okay. Thank you, class, and thank you for this 1 extra minute. I'll see you on Wednesday.